So, redox reactions that's a short form for reduction oxidation reactions. Uh, Oxidation originally in the first unit when we talked about organic chemistry meant combining more carbon-oxygen bonds, and reduction meant combining more carbon-hydrogen bonds. That worked for organic chemistry, but the more accurate and broader definition is that oxidation is losing of electrons and reduction is the gaining of electrons. So a little acronym, LEO goes GER, means that losing electrons is oxidation and gaining electrons is reduction. Something that can help you remember oxidation reduction reactions. And oxidation is the loss of electrons and the reduction is the gain of electrons. So you'll often see oxidizing agent and reducing agent described. The oxidizing agent is the electron acceptor. It is actually the species that is being reduced. Because it is an agent, it is causing the loss of electrons and thus accepting them. And then the reducing agent is the electron donor causing the reduction, and thus also the species that is being oxidized. Sometimes those two can be mixed up a bunch. So half reactions are how we can determine which elements are being oxidized and which are being reduced. It's impossible to have one without the other. Think of losing electrons, they're going to go somewhere. So you have to have the same number of electrons being lost as you do gained, and thus you have to have an oxidation and a reduction reaction happening at the same time, and that's why we call it redox. So here's an example of iron oxide combining with aluminum. The iron changes from an oxidation state of 3 plus to 0. We're going to talk about these oxidation numbers in 1 second. And the aluminum goes from 0 to 3. So if you wrote the half reactions, iron, which had a positive charge of 3, is gaining 3 electrons and thus being reduced. Aluminum is making aluminum oxide and thus being aluminum 3 plus to show the oxidation. I've written the reduction and oxidation half reactions slightly differently. You could, in this reaction here, write Al 3 plus to just show that aluminum is being oxidized. But you can also show that in this compound, the Al3 plus balances with the negative charge of oxygen. Iron would also have oxygen in this overall reaction, but purposely they're shown as two half reactions in different ways because both are correct. The oxidation number of oxygen is -2 in both of these cases. Thus, oxygen is not being reduced or oxidized. And notice that you have 3 electrons being gained and 3 electrons being lost, so the reaction is balanced. You can look at oxidation and reduction as a movement up and down or scale. So the oxidation number would increase with its oxidation state, +7 and -7 being the highest and lowest on that scale. So there's a bunch of rules, and you have to keep track of electrons and count these rules, and they're hierarchical, which means that if you get to the first rule and you can assign an oxidation number to an element based off of that first rule, then you stop there and you move through the hierarchy as you're assigning numbers to these elements. We're going to do a few examples and I'm going to talk through the rules, and then there's a bunch of examples on a worksheet. So, and then they're hierarchical. So, number 1, the oxidation number of all atoms and compounds must add up to 0. So if it's an atom or a compound with no charge, they add up to 0. We kind of break number 1 down. Free elements, so if you just had a solid potassium or gaseous chlorine, means that the oxidation number is 0 for potassium and chlorine in that example. All oxidation numbers of neutrons must add up to 0, so look at our aluminum oxide example. The aluminum has to be 3 plus and the oxygen has to be 2 minus to show a net charge of 0. You multiply the charge just like when you were doing nomenclature questions. So the overall oxidation number of that compound is 0. However, aluminum's oxidation number is 3 plus and oxygen's is 2 minus, based on rules further down in the hierarchy. All oxidation numbers that are polyatomic should add up to the charge of the polyatomic ion. So hydroxide has a negative charge, meaning oxygen and hydrogen's oxidation numbers have to add to -1. In that case, oxygen here will be, it should be 2 minus and hydrogen 1 plus. The signs are reversed in that, so you can make that change in your notes. For a single atom, oxidation number is always equal to the ionic charge, so if you just have sodium ions, then the sodium has a positive 1 charge, so sodium's oxidation number is +1. And chlorine's would be -1 if it was just a chlorine ion. Okay, moving on to the second hierarchy. So number 1 kind of sets the grounds. Then, fluorine has an oxidation number of -1, period. No exceptions except for fluorine gas. When it's F2, because the first rule in the hierarchy is that fluorine has to add to 0, that would be the only exception where fluorine exists with an oxidation number of 0. And then you move on and it would be -1. Non-transition metals have oxidation numbers corresponding to their charge. So, alkali metals will be +1, alkaline earth +2, yttrium, scandium, and aluminum have a +3. So if they're not in that transition block, they're 1, 2, or 3, just like the charges that they always contain. And that's rule number 3. Rule number 4 is hydrogen, and hydrogen is nearly always +1. There are a few exceptions when rules number 1, 2, or 3 come first. So you can think of the H2 example, that would mean hydrogen would be 0, but also if you have a hydride, like calcium hydride or sodium hydride, then rule number 3, where the alkali or alkaline earth metals take priority, would combine with rule number 1, where you have to add the charges together to give hydrogen a -1 oxidation number. So in this sodium example, because under the third rule, sodium will have to be a +1, and based off of your first general rule, the compound has to add to 0, hydrogen would have to be -1. It could not be +1, or that compound would have a +2 charge, which it doesn't. Rule number 5, oxygen in a compound is nearly always -2. There are 3 examples there. They're very similar to the other exceptions we've already looked at. Again, if a previous rule supersedes the rule, that's what you go with. 6, elements of group, you can say group, elements of group, and this would be, in this case, 17, 16, and 15. My Roman numeral brain just got messed up there for a second. Sorry, group, I think the A was throwing me off. Group 17, 16, and 15. So the halogens and then like oxygen, sulfur, they're going to be -1, -2, -3, respectively. So we're looking at a bunch of nitrogens, and it has a bunch of different oxidation states based on what it is bonding with. So it's oxygen in a lot of these cases, and oxygen's rule supersedes the nitrogen rule, which would be the 8th and final rule. So here you have 3 oxygens at -2. There's 3 of them, so that's a total charge of -6. The nitrate ion has to have a -1 charge, so nitrogen has to be +5, because +5 plus -6 is -1. You can follow that logical reasoning throughout all of these examples to see how nitrogen can form all those different oxidation states. Carbon is also very versatile. In the first one, like carbon, solid carbon like graphite or diamond would be 0. Carbon monoxide, because the oxygen is -2, would be +2. Carbon dioxide, again, oxygen is -2, so carbon would be +4 in this case. You have methane, and hydrogen's rule is that it is +1, so carbon is -4 in this place. Then you have the combination of a compound where hydrogen is +1, and there's 2 of them, and oxygen is -2. Those already cancel each other out. Carbon is 0 again for number 5. And then you have carbonic acid here, where it's -6 provided by the 3 oxygens and +2 provided by the 2 hydrogens, meaning carbon would have to be +4 again. So you're starting to understand why you look at the periodic table and you see all those different oxidation states that could be listed, especially for non-metals. This is why. So what do these numbers actually do for us? So here's another example. You have iron 3 dichromate and +3, +6, and -2. I can just go through them there, and you can pause the slide and look at the example and the explanation here. I'm going to move on to why balancing redox reactions uses oxidation numbers. And one of those reasons is it's sometimes tough to balance without a plan. Take this example. You have KMnO4 plus H2S plus H2SO4 giving K2SO4 plus MnSO4 plus S plus H2O. If you're going to balance this just by inspection, so this would be like your grade 11 rule where you try and plug in numbers, it is really difficult. I suggest in class usually when I do this that you try it. And very few people actually reach the properly balanced equation doing it this way. However, if you use the oxidation rules and the oxidation method, we can go through and balance this. I'm going to take this balancing up in a different video. So give it a try. Here are the rules for balancing using oxidation numbers. The method is useful when complete reactions are given. So write the complete equation and assign oxidation numbers to all of the elements. Then identify the element that is being oxidized and the element that is being reduced. So if it's an oxidized element, the oxidation number will increase because it has lost electrons, becoming more positive. And if it is reduced, then the oxidation number will decrease because it has gained electrons, becoming more negative. Use lines to connect the elements being oxidized and reduced. So we're going to see that in the example. Show the charge in oxidation number. Then make the total change in oxidation number equal. Electrons gained must be equal to electrons lost. You cannot have extra electrons either being lost or gained, so those oxidation numbers would have to balance out. Balance the remaining atoms by inspection. And let's do an example. So here we have, that came up first. We have iron oxide combined with carbon monoxide to create solid iron and carbon dioxide. The oxidation numbers have been assigned as +3 for iron in the reactants and 0 for iron in the products. So iron is changing. Carbon will be +2 in the reactants and +4 in the products. So carbon is changing as well. Oxygen is -2 in all 3 compounds that it exists in, so it is not being oxidized or reduced. Here we've connected iron. This is what I meant by that step saying draw lines to connect those. Because iron is changing from +3 to 0, it has gained 3 electrons, and because carbon goes from +2 to +4, it has lost 2 electrons. Lowest common multiple of 3 and 2 is 6, so this has to happen twice, and this has to happen 3 times, so that 6 electrons are both gained and lost. Put the coefficients in to balance these equations. You have the 2 here to balance the fact that iron is 2 in the first reaction, and that makes the iron gain 3 electrons twice. Here, you're going to put the 3 in on both the carbon monoxide and carbon dioxide so that carbon loses 2 electrons 3 times. Just like that. Check if the oxygen is balanced, and that is a balanced equation. This one was fairly simple and could probably be done by inspection. Watch my other video for an example from the one that I provided a few slides ago.